In this video, I'm going to talk about Nilpotent groups by first introducing some preliminary information and idea of subgroup constructions, which link to the definition of nilpotent groups. And in the last part, I'm going to pose a question with examples for the sake of time. So before jumping into the definition, I'm going to talk about two information. The first one is the center of the group is defined as the set of elements in the group such that it commutes with all elements of G, and which is actually a normal subgroup of G. And the second one is that if a subgroup N is normal in G, then we can think of a quotient group G mod N. And also every subgroup of G mod N is of the form H mod N, where the H is a subgroup of G containing N. And you can easily check that H is also a normal subgroup of N based on this fact. So these are all things it might be helpful to know. And I'm going to talk about the idea of subgroup constructions, which will be linked to the definition of nilpotent groups. So what we're gonna think about is a series of subgroups from the smallest. So obviously, a trivial subgroup, identity subgroup, is the smallest one. And also the center of the group G is a subgroup of G, which contains the identity subgroup. And we want to build up a subgroup of G which contains the center and so on. So first, we are going to consider the quotient group G mod, the center of G. So here we are going to consider center of this quotient group, which is the Z of G mod Z of G. Since it is a normal subgroup of the quotient group, we can think of this subgroup as subgroup mod the center, which is from this fact number 2. So let's call this subgroup of G as Z prime of G. And this subgroup, Z prime of G, has to be a subgroup of G containing the center. So we found another subgroup, Z prime of G, which contains Z of G. Similarly, we can consider another subgroup, Z double prime of G, where the center of this quotient group is equal to Z double prime of G mod Z prime of G by using this fact as well. And this Z double prime of G is going to be a normal subgroup of Z prime of G. So is a subgroup of G containing this subgroup. So we can build up again another subgroup of G containing Z prime of G. So if we define the subgroup of G recursively like this idea, we can think of a chain of subgroup as follows. So G is a group, and define the following subgroups recursively as above. So we're going to start with Z0 of G, which is going to be identity subgroup, and Z1 of G as the center of G. And then for any natural number I, we're going to define Zi plus 1 of G as a subgroup of G containing Zi of G, where the center of this quotient group is going to be equal to Zi of G mod Zi plus 1 of G mod Gi of G. So now we have the chain of subgroups from the smallest one, Z0 of G. And this chain of subgroups is called the upper central series of G. Now, we might have a question as, would there be some natural number I such that Zi of G is eventually the whole group of G? So from this definition, we don't know whether there is a subgroup like this, but if there is a natural number I such that Zi of G is equal to the whole group, then we are going to define G as called nilpotent now. And you can see that if Zi of G is equal to G, then Zi plus 1 of G, since this contains Zi of G, and which is the whole group, then this is also going to be equal to G. So the smallest such I will be called the nilpotent class of G. So this is the definition of the nilpotent group. And now that we have talked about the definition of nilpotent groups, I'm going to show you some examples of whether a group is nilpotent or not. And for the sake of time, I'm going to pose questions as to why. So the first one is that if a group is abelian, then it has to be a nilpotent of class 0 or 1. For the Y part, you can consider the center of a group and combining with the definition of nilpotent group. And for the second one, if the group is not trivial and the center is an identity group, then G cannot be nilpotent. Y part, for the Y part, you can consider Z2 of G from Z of G. You can construct Z2 of G and you can see why G is not nilpotent. And following number 2, you can also conclude that the symmetric group S sub 3 is not nilpotent. That's all for this video.